One of the main categories of execution plan operations are the operations used to access data in tables. These are important to understand because how Oracle retrieves and subsequently processes the data needed by your SQL statement is one of the primary drivers of performance. What you want to keep in mind is that you want to structure your SQL where Oracle can retrieve and process as little data as possible. This is simple common sense. If Oracle has to retrieve a large number of rows, process through all of these rows, and end up throwing most of them away, this is going to be inefficient, and that inefficiency will show up in the response time of your SQL statement. The first operation we will take a look at is a full table scan. In execution plan output, you will see the words reversed so it reads table scan full, but pretty much everyone in the database community refers to this as a full table scan. In this scenario, Oracle is going to read every block for the table and process each and every row in every block. If some of the blocks for the table are in Oracle's buffer pool, then Oracle can read those blocks from memory. For all of the remaining blocks, Oracle will need to read those off of disk, causing physical I/O to occur. The need to perform this physical I/O, and especially because this potentially could be a large amount of physical I/O, is one of the primary reasons why a full table scan is generally regarded as the most expensive operation that can be performed as part of a SQL statement. If a table takes up several thousand or tens of thousands of blocks on disk, it is highly likely that Oracle will have to read a majority of those blocks from disk. As we know, reading data from disk is comparatively very slow when compared to reading blocks from the buffer pool. And if we need to read several thousand blocks off of disk, this is going to have an adverse impact on performance. If Oracle does need to read data from disk for a full table scan, it will perform what is called a multi-block read. That is, Oracle doesn't just read one block at a time, but just like the name implies, will read multiple blocks for the table on each I/O operation. Reading multiple blocks together in this way will be more efficient. However, if the table is large, there will still be a significant I/O cost to performing the full table scan. The other aspect to consider is that when Oracle is performing a full table scan, it has to process through all of the data in the table row by row. So if a table has 100 million rows, this is clearly going to take some time. The picture to have in your mind here is a sequential scan type operation. Just like if you were in a language like C# or Java, and you were iterating through each element of a very large array. If the array that we're iterating through has 10 million or 100 million elements, not only is that operation going to take quite a bit of time, but we are also going to expend quite a bit of CPU working our way through an array of that size. These same principles apply in Oracle. For a large table, we want to avoid a full table scan operation because what is really happening is a sequential scan of the data where Oracle is having to examine each and every row on the table. There's an important distinction, though, that for small tables, performing a full table scan is perfectly fine and may even be the most efficient operation. You will notice on many of your smaller lookup type tables that even when an index is available, Oracle will often just perform a full table scan of these tables to get the data that it needs. What is happening here is that Oracle knows that if a table is small enough, it is more efficient just to read the table and find the data that you need, rather than going to an index first and then correlating the results from the index back to the table. I mention this because full table scan operations are one of the main things you look for when troubleshooting a poorly performing SQL statement. However, for small tables, performing a full table scan is common and probably the most efficient choice, so you don't need to expend effort worrying about why Oracle is not using an index in these cases. The next operation to look at is a table access by index row ID. In this case, Oracle has the row IDs of the rows that are needed, probably from an index lookup operation that preceded this operation. By having the row ID, Oracle is able to first access the specific block and then directly locate the required row inside the block that contains the needed data. Oracle can do this because an Oracle row ID contains information both about the block where the data is stored, as well as the exact location of the row inside of the block of data. So you can see this is going to be very efficient because Oracle is able to directly go to the row that contains the data that it's looking for. As before, if the needed block is already in the buffer pool, Oracle can simply fetch the block from memory. If the block's not in the buffer pool, Oracle will need to perform physical I/O in order to retrieve the block. However, since we're only retrieving blocks that contain the data we need, this is a much more efficient operation than a full table scan. Even if Oracle does need to read some blocks from disk, the number of blocks to be read are significantly fewer than in a full table scan operation. When you are reading table operations in execution plans, you will often see a filter predicate listed along with the operation. In this example, we see a filter predicate on the zip code column being applied in the full table scan operation. What a filter predicate is telling you is that Oracle is first reading the data and then applying the filter to the data in order to only keep the rows that are needed for this operation. So in this case, we don't have an index on the zip code column in the applications table, so Oracle is having to read all of the rows of the applications table and then is applying the filter to only keep the rows from zip code 90017. Filter predicates are not only applied to full table scan operations, but also can be applied to table access by row ID operations. In this example, Oracle is using an index on the students table to find the records with this particular zip code. However, the index as defined is only on the zip code column. So in order for Oracle to then find all the students with the last name of Jones in this zip code, Oracle first has to read the corresponding rows in the students table by use of a table access by row ID operation, and then apply a filter predicate in order to find only the rows with the last name of Jones. It is normal to see some filter predicates on table operations in this way. After all, you're not going to have an index on every column. In this case, Oracle is using the index on the zip code column to narrow down the rows that it needs to examine to a small subset, and then apply a filter predicate only to this small subset of rows in order to retrieve the specific rows that it needs. So when you see a filter predicate listed in an execution plan, keep a couple of things in mind. First, the filter predicate is being applied after Oracle has read the rows, and Oracle is applying this predicate to all of the rows in that data set. Therefore, we want to make sure that the target data set that Oracle is applying the filter predicate to is as small as possible. So if the filter predicate is being applied to a full table scan, you should probably investigate the situation to see if an index can be added so that Oracle can access only the subset of the data that it needs to, and not every row in the table. If a filter predicate is being applied to a table access by row ID operation, then the predicate is only being applied to a subset of rows. This is normal behavior, as Oracle is applying the filter condition only to this smaller subset of rows after it's performed an index operation.